Hello, physics students. I am Mr. Williams, and we're going to talk about electromagnetism again. So this is going to be part two. In the last lecture, we talked about what is electromagnet, how can you make the electromagnet stronger, what are the properties of electromagnets. Remember that if you put current, which is the flow of electricity in a certain direction, if you put current down a wire, what's going to happen is you're going to generate a magnetic field. If you did it in a straight wire, you would get a magnetic field with the north and south pole, but it'd be pretty weak. But if you made a loop, then it'd get a little bit stronger, and the north and south pole would be a little bit stronger. But if you did many loops, and then it would be much stronger. If you added a piece of iron, put like an iron cylinder, and then wrapped all the coils around that iron cylinder, it would be an even stronger magnet. And so as you add more turns, as they call it, more coils, you get stronger magnets. And another way that you can make it stronger is to add more electricity. And so as we have used electricity to create magnets, a temporary magnet, as long as that electricity is there, there's going to be magnetism there. It's got a north and south pole. And let us not forget that when you have the same poles near each other, they repel. So if you have a north and a north, they repel. If you have a north and a south, they will attract. And so we can use permanent magnets in conjunction with electromagnets to push and pull each other. So this helps us induce motion. Well, one of the coolest ways that we use this is in speakers. So speakers contain an electromagnetic coil connected to a flexible speaker cone. The electromagnet changes electrical energy into vibrations of the speaker cone to produce sound. So let me describe this animated GIF here. But at the bottom, this little gray cylinder, that is a permanent magnet. All right, it says it right here. It's a permanent magnet. Okay. There are what we see right here, that copper coil, well, that's going to be your electromagnet. And so electromagnets, since they produce north and south poles as electricity is going down through them, it will either be pushed up away from the permanent magnet, because the permanent magnet does not change its north and south poles, or it'll be pulled back down and attracted by the permanent magnet, depending on what direction that electricity is going. Remember, if you want to turn a north pole into a south pole with an electromagnet, you just reverse the direction of the current. Okay. There are some other parts of the speaker which aren't really too important for us. They have what they call a diaphragm. That's just it's like a big piece of paper that just pushes the air back and forth. And it's got dust caps to keep it clean. This is a voice coil, which is to help increase the magnetism of the speaker coil, of the solenoid of the speaker coil. And it's suspended on something, and it's sitting in what they were calling a basket, and has something called a spider, but don't worry about that. Think about the electromagnet sitting in a permanent magnet. So changes in electric current causes changes in strength and direction of the magnetic field in the electromagnet. You want more volume? Add more electricity. The electromagnet is surrounded by a fixed permanent magnet. Okay, just like I described earlier, there's the fixed permanent magnet down here. And the electromagnet is just kind of hovering right on top of it. It's suspended by this basket and this kind of like paper cone right here. And so when the changing directions of the magnetic field causes the electromagnet, that's what EM stands for, causes the electromagnet to move back and forth, causing the speaker to vibrate and reproduce sound. Like, that's how a speaker works? Yeah, that's how a speaker works. That sounds pretty simple as long as you know what's going on with the electromagnet. Yeah, it really does. It's kind of amazing that it just works at all. You have an electromagnet. Electromagnets have north and south poles. You sit it on a permanent magnet and you glue a piece of paper around it, like they're calling it a cone, right? And as electricity goes back and forth, it vibrates up and down. And if you use the encoding of a speaker, those electrical charges will be in the same shape and vibration of your voice. And so that's how we get a speaker. Really neat stuff. Now, so if you have an electromagnet, if you have an electromagnet and you are putting it near a permanent magnet, what's going to happen, right? Let's just say that the blue is the South Pole and the red is the North Pole. Okay, so when current flows into the solenoid, remember this wire coil is a solenoid, like poles of the electromagnet are repelled and attracted to the poles of the permanent magnet. This causes the electromagnet to rotate. So as this is sitting here on the rod, this rod is rotating freely, right? And so as electricity goes through it, then the south pole of the electromagnet is going to be pushed away from the south pole of the permanent magnet. And then the south pole of the permanent magnet is going to be attracted to the south pole of the electromagnet. The south pole of the electromagnet then would be attracted to the north pole of the permanent magnet. So it gets pushed away over here and attracted over here. So the magnetic forces on the electromagnet causes it to rotate until it's aligned along the field lines of the permanent magnet. And then the rotation stops. Oops, sorry about that. If you wanted it to continue to rotate, what would you do? Did you say you would reverse the direction of the current? Yeah, because all of a sudden, this blue one represents the south pole right here. If you reverse the direction of the electricity, which is not shown in this image, but if you reverse the direction, all of a sudden this would turn to a north pole and then it would be pushed away by the permanent magnet and attracted to this side of the permanent magnet. And so then we have a rotation. And that's the basis of a motor, how a motor works. So the forces exerted on an electromagnet by another magnet can be used to make the electromagnet rotate. The poles of the EM, the electromagnet, are repelled by like poles and attracted by unlike poles of a permanent magnet. So it's just like if you got an electromagnet, it behaves like a permanent magnet as long as there's electricity. And then all you have to do is change direction of electricity, and then you reverse the north and south pole of the electromagnet. Neat. Permanent magnets, they don't reverse. An electromagnet will rotate until its poles align with opposite poles of the permanent magnet. Permanent magnets are not, speakers, for example, are not difficult to make. Motors are not difficult to make. Making them well, I guess that makes a little bit harder work. But there is definitely a space for people to start their own businesses in the United States of America, as we have moved a lot of our jobs out of the country. And there's a lot of space and a lot of people that want demand of made in the USA products. And it's not difficult to make this. And if you could make this, you could sell it. And if you could break even, you could break a profit. So we have this device called a galvanometer. That's how I'll say it. Some people say galvanometer. Whew, tripping over words. I say galvanometer. Some people say galvanometer. I go with galvanometer. It just works for me. I learned this word by reading it. So galvanometers are devices that use an electromagnet to measure changes in electric current. Examples include a car's fuel gauge and a engine temperature gauge. So how does this work? So basically, we have a north and south pole permanent magnet. And then we have some kind of electrode. And an electrode is a electronic component that provides a electric current depending on what you're doing. That it could be that it's heat's creating electric current, or its position as it's floating in a fluid is creating electric current. Whatever, it's creating electric current. And so the electric current, what it does is it powers an electromagnet. Okay, and the electromagnet will rotate based on how strong the current is. And so right here, you can see like this arrow that's attached to it. It's just a little rod, and the rod is attached to the electromagnet. So let's say it was originally here. As the electromagnets rotate, it would then move over up to here because the magnetic field that's being applied because the electricity in this device is pushing it over. So a manometer. There's an electromagnet inside. As electricity is going through it, it will cause the electromagnet to rotate. Well, that rotation of the electromagnet just causes the meter, which is like the arrow right here, your gas gauge, for example, it just causes it to move with the electromagnet. Electromagnet moves, then the meter moves, and that's how we can measure and gauge how much electric current is in a device. If you get an old time electric meter, there's digital meters now, but you get the ones that are not digital and you want to test, say, a car battery to see how much electricity is going through it, or you're you're an electrician and you want to test if something has electricity in it, you use a galvanometer, right? But they look a lot nicer than this depiction. So what's an electric motor? Well, electric motors are devices that use magnetic forces between an electromagnet and a permanent magnet to make a shaft rotate. So if you remember that image from the how to make an electromagnet rotate, you can use the charge of an electromagnet to create north and south poles, and they will either push or pull on a permanent magnet. And so as you have a push and pull, you can make those permanent magnets rotate. You put those on a rotor, attach some fan blades to it, and then all of a sudden you have a ceiling fan. Okay, so this is an example of an simple electric motor. Okay, this is a electronic trying to think of the words. Whenever you study electronics, this would mean a power supply right here. And so the power supply is providing electricity to this. All right, I'm going to pause this right here. All right. So right now, electricity is being applied to each of these wires. So if you look carefully, this side, okay, this wire is not connected. This is not a square, right? One side is not connected to the other. There is a gap between this circle right here, this rotor, I guess you could call it. You call them brushes. No, they don't. They call them split ring commutator. So as you have a gap here, and you have a gap here. Okay, that's so you can separate the poles of the electromagnet. So as electricity is going through here, this side of the electromagnet will be, let's say, a well, right now it would be a north pole. And so as it's a north pole here, since there's a permanent north pole magnet to it, a north and a north, it will push, so it'll push it away. Well, on the opposite side, at the same exact time, you have a opposite current, say negative charge here. The negative current is going over here, and so it is a south pole. So the south pole magnet is also pushing it away. So as the North Pole is pushing it away and the South Pole is pushing it away, it'll cause it to rotate. Okay. And so as it's rotating, okay, right here, there would be no charge, and we're just using the inertia, the already existing motion of the electromagnet to continue to move. Right? And then every time it goes past the gap, it will change. Let me get an image of this gap. All right, hard to pause it. Okay, then the gap right here, every time it goes past this gap, a different charge is going through it. So we have our positive electrical charge, your negative electrical charge. Every time it goes through that gap, it touches a different charge, and so the north and south pole switch. And because we have this constant north and south pole switching of the motor, it causes motion. It's always being repelled. It's always repelling and attracting, repelling and attracting, repelling and attracting, because we have a clever design, so an engineered piece of equipment to cause it to constantly change the direction of the north and south pole of the electromagnet, which causes motion. So in a simple electric motor, a coil rotates between the poles of a permanent magnet. To keep the coil rotating, the current must change directions. The changing current alternates the north and south pole in the electromagnet. The alternating poles in the electromagnet allows the electromagnet to constantly be pushed or pulled away from the permanent magnet. The motor that we build is different because the current switches on and off to prevent the poles from lining up and staying that way. So if you are coming after spring break to the in-person sessions, we are going to build a simple electric motor. It's going to be awesome. And this will be the electric motor that we build. It's going to be fun. Hope to see you there. Okay, so this is some images out of your textbook. I want you to write the step 1 and step 2. There's going to be a step 3 and 4, and this is going to be how we make a motor spin. Right? So batteries are power source. The commutator, that is the circle that's got 2 holes broken in it. So every time the brushes, that's just where the wires are touching the thing that's rotating. The commutator, as it's touching the commutator, it allows electricity to go through, and every time it passes the gap, that gap causes a switch in the north and south poles, because it'll have a, when it used to have a negative charge going through it, it now has a positive charge. Okay, but when a current flows in the coil, the magnetic forces between the permanent magnet and the coil cause the coil to rotate. Step 2, in this position, the brushes are not in contact with the commutator and no current flows in the coil. The inertia of the coil keeps it rotating. For step 3, the commutator reverses the direction of the current in the coil. This flips the north and south poles of the magnetic field around the coil. And in step 4, the coil rotates until its poles are opposite the poles of the permanent magnet. The commutator reverses the current and the coil keeps rotating. It's a very clever design using what you know about electromagnetism. All right, guys, that's all we're going to talk about for now. A couple things to keep in mind. Since this is the last week before spring break, and after spring break, we'll have a choice of virtual learner or in-person learner. So this week is going to be a week where a lot of teachers are going to be working inside the building, so there are not going to be any live classes, okay? So there aren't going to be live classes this week. It's all going to be asynchronous due contact me with your questions, your comments, your concerns, because I'm here to help you guys. Have a great day. Let me know what you need. Bye.